All right, so for 10D, we're going to focus on actual regression models, but just first, we're going to ease into it by kind of reviewing what we did in exponential growth and decay. So here's another real life application. I tried to do some research before I actually made this problem, but just based on some loose research, this is what I found. So the bee population is approximately 2.75 billion as of 2016. Nope, I can't read. 2016, but is declining dangerously at approximately 60% per year. So this is just kind of standardized to kind of fit the exponential growth and decay model. However, the actual population of bees has been kind of fluctuating. So just kind of starting off, does the scenario represent a growth or decay and justify? So this is a decay. The population of bees is decreasing. All right, so now we want to write an equation to model the scenario. So keep in mind, this is 2.75 billion. So if you want to write it out as an exact equation, you'd actually have to write out the 2.7 billion. But in terms of writing it out this way, so you could write it out this way if you want to do it in terms of billions. Or if you actually want a more exact and precise way, then you could also write it out in terms of, this will be fun, 275 and 1 minus 0.6 t, which means 275,000,000,000.4 t. All right, so really the second equation over here is what I'm going to be modeling and using just to kind of put it in more perspective, kind of give you a better estimate as the population is actually changing over time. So we want to know what's the population after just 5 years, if the population is continuously decreasing at 60% per year. So that means our t value is going to be 5. So I'm going to go ahead and just copy the equation up here exactly how it is. However, that means the t value is then going to be 5. So I'm going to plug this in. You could use your calculator, whatever. All right, then 0.4 raised to the 5th. So that means after 5 years, there's going to be exactly 2816. Nope, I didn't get my commas right. $28 million. There we go. 28,160,000 bees. Right. So just after 5 years, we went from 2.75 billion to 28 million. So just in 5 years, it's decreased dramatically, which is very dangerous. And that's only 5 years. So this will also kind of transition into the wildlife information of what's considered endangered, what's considered extinct, and all of that jazz. But we're going to save that for bio and whatnot, or wherever you learn it. All right, so if the bee population continues to decline at its current rate, after how many years would the bee population reach extremely critical levels of less than 100,000 bees worldwide? So this is kind of going back and using the table. So let's actually use the Casio for this part. So let's go ahead and open that. Hello. There we go. Okay, now that that's going. All right, so here's your Casio. All right, so I'm going to go to the table and I'm going to plug in the function. So 275 million thousand. Then we have 1 minus 0.6. And that's going to be raised to the x. So this is our equation. So we want to find when is it going to reach less than 100,000. So right over here, 11 and 12, because at 11, we're going to have approximately 115,000, whereas after 12 years, we're down to 46,000. So it's going to be after 11 years, or between 11 and 12 years is going to be the time frame there. All right, so come on, where are you? There you are. All right, so looking at the table, it's going to be after 11 years, or between 11 and 12 years. Okay, so that's just kind of a recap of exponential growth and decay. So now we're going to get into the regression models, which is going to be a little bit different. So we've actually done this before. We're just kind of throwing everything into one. So regression models are really just about analyzing data. So this is kind of a, not really statistics, but kind of along the general guidelines of statistics. So we want to analyze the change in X and Y values to find a pattern. So when I say pattern, the only patterns that we can have are going to be addition and multiplication. So we actually cannot have subtraction or division. But because we can't have subtraction or division, we do have some loopholes that we can use. So if I can't subtract, what I can do is I can add a negative. So it's still addition, but it follows the same guidelines of subtraction. And then I can't divide, but what I can do is multiply by a fraction. So I can't divide by 2, but I can multiply by 1/2. So it still follows the guidelines of multiplication. So the reason that is because of the patterns. So we can't have add, subtract. We have to have add. We can't have add, division. It has to be add, multiply. All right. So there are some patterns that we're going to be looking at in our tables, and it's going to tell us what kind of regression that we're going to be looking at. So one thing I will say is we have actually done linear and exponential and quadratic over the course of this year so far. One equation that we have not done, but I just want to kind of introduce the idea to everyone, is the idea of a cubic function. So this is just to kind of show a pattern. So patterns from tables or coordinates that we'll have are going to follow an add pattern for linear, an add multiply pattern for exponential, an add second difference pattern for quadratic, and an add third difference for a cubic function. So it is so crucial and imperative that you have a calculator for this one, because this is a calculator lesson. Everything's done in the calculator. You can do these regressions by hand, but I don't recommend it. We've actually done the linear, exponential, and quadratic by hand. I do not recommend doing a cubic by hand. It is a long, tedious process. So, all right, we're gonna go ahead and dive in. So because it is all based on the calculator, I've actually put in the steps on both a Casio and a TI calculator. So if you have the Casio, which is provided by the school district, then follow what's on the left. If you have a TI, follow the steps and the functions on the right. Casio on the left, TI on the right. So I'll let you guys follow those guidelines, but I'm actually going to use the Casio steps as we solve these problems. All right, so we want to find the function pattern, the function type, and the function rule. All right, so I'm going to kind of use number one as kind of a skeletal structure. All right, so kind of looking here, looking at the change in X, it's always going to be addition. All of our patterns are going to start with addition. So really, you just need to look at the change in the Y values. So if I'm looking at the Y values, to go from 2 to 3, that's +1, 3 to 4, +1, 4 to 5, +1, 5 to 6, +1. So what that means is for our pattern, this will be an add pattern. And an add pattern, if you look back up here, is going to correspond to a linear function. So this is going to be a linear regression that we're going to do here. So regression is just a fancy way of saying we're going to find the equation. So an add corresponds to a linear equation. And then the actual function rule is what the calculator is going to do for us. So when I say rule, This is the equation. All right, so highly recommend keeping this problem handy. I'm going to switch over to the calculator. Okay, I don't need this garbage anymore. Just kidding, the B's are not garbage. All right, so what I'm going to do is I'm going to go back to the menu. So on my menu, I want to be able to do a regression. So a regression means I need to go into statistics. So in statistics, press enter, and it's going to bring up lists. I do not want these values. I'm going to delete these values. All right, so in L1, in list 1, you want to input all your X values, and then in list 2, you want to input all your Y values. So that's subtraction. All right, so I want to do -2, -1, 0, 1, and 2 in L1 or list 1. And then in list 2, you're going to input all your Y values. So 2, 3, 4, 5, and 6. So you essentially are going to copy and paste your entire table into the calculator table. Now, once you input all your information, you actually want to do a regression. So to get there, you want to press calculate, which is F2. And then we want to do a regression. So REG is the abbreviation of regression. So press F3. So when you get to this part, now it's going to give you the different types of regression models. So if you do X, that's linear. If you do X squared, that's quadratic. X cubed is cubic. X fourth is quartic. And then they have log, which is logarithmic, exp, which is exponential, power, which is a power function, sine, which is a sinusoidal, a logistic, which is something else, no idea. But you can use F6 to toggle between the two menus. And we know this is going to be an add, which is a linear pattern. So a linear pattern means you want to press F1. And now it's going to toggle or populate AX plus B or A plus BX. AX plus B is slope intercept form. A plus BX is more of a business model. So you want to press F1. So now it's going to give you your A and B value for your linear equation. So it tells you your A value is 1, and then your B value is 4. So our equation is y equals 1x plus 4. And we don't have to write that 1, so you could just write y equals x plus 4. All right, so if I go back to the iPad, not sure why it does this. Okay, so if you go back over here, we have an add pattern, which follows a linear pattern. And then once I do the regression in the calculator, it gives you the function rule of y equals x plus 4. All right, so just FYI, the work to show on these problems is really going to happen in the table. So I need to see like the add multiply, add second difference, add third difference. That's what I need to see in the problems. All right, so over here, number 2. So looking at the y values to go from 1 to 3, if I try to add 2, it doesn't work when I try to do it here, which means adding is not going to work. So I have to try something else. All right, so the other way to go from 1 to 3 is if I multiply by 3. So multiplying works for everything. So you have to have a clear, consistent change throughout the entire table process here for it to count. So if I do times 3 times 3 times 3 times 2, it doesn't work. It has to be the same throughout the entire problem. All right, so our function pattern here is going to be add, multiply, and an add multiply pattern is going to be exponential. All right, so I'm going to follow the same steps as before, but instead of pressing F1, I'm going to toggle over using F6 and then press F2, I think, F2 or F3. Why? Okay, so I'm going to go back over to the Casio, and now we're going to do a exponential regression. So I'm done with this menu, so I'm going to exit. And now I just need to change the table to match. So the X values are good to go, so I'm going to leave those. I just need to change the Y values. So I have 1, 3, 9, 27, and 81. All right, so once you get the table input, we want to do a regression. Oh, why is that menu still there? Exit again. There we go. All right, so I want an exponential, so it's not on this menu. So I need to press F6 to toggle over. Yep, and then F2 is going to be exponential. So press F2, and then we want to press F2 again. We do not want that first one. All right, so now our equation here is going to be y equals a, which is 9, times b, which is 3, raised to the x. So y equals 9 parentheses, 3, raised to the x. This is going to be a lot of going back and forth between the iPad and the calculator, so please have some patience. All right, so there is our equation for exponential. So kind of like I said before, this is all in the calculator. However, between the linear regressions and the exponential regressions, we've actually done those before. So if you want to do those by hand, you go for it. All right, so number 3 and number 4. All right, so these are going to be the more kind of tricky ones. All right, so just to start off, remember, we're looking for a clear, consistent change in both the x and the y values. So if I go from -6 to 0, that's adding 6. And if I go from 0 to 8, that's adding 8. Then 8 to 18 is plus 10. And then 18 to 30 is plus 12. So notice how we still have no clear, concise change. All right, so what I'm going to do is I'm actually going to go another level. So now I want to find the change between 6 and 8. So between 6 and 8, that's plus 2. Between 8 and 10, that's plus 2. And between 10 and 12, that's plus 2. That's not a 12. There we go. So now if you look here, now we have a clear, consistent change. So what this is called right here, nope. This is called a second difference. All right, so what this pattern is going to be called is add second difference. So we're going to have add, and then second difference. All right, so an add second difference pattern, what that yields is a quadratic function. All right, so we're going to have a parabola from this table. All right, so now what I'm going to do is go back to the calculator. And I'm going to do a quadratic regression. So exit, exit. Nope, back to regression. All right, so in this case, my x values changed. So 0, 1, 2, 3, 4. And then my y values over here, we have -6, 0, 8, 18, and 30. So I know I'm going to have a quadratic regression, so I need to press F3 for x squared. And here's your equation. So y equals 1x squared plus 5x minus 6. So y equals, so just x squared plus 5x minus 6. So back in unit 9, I believe, we actually did quadratic regressions by hand. So if you are more than comfortable doing it by hand, you still can do it by hand, but I will say a calculator is going to be quicker. All right, so there's the quadratic regression. So now we're going to go back over here. All right, let's do number 4. Why is this screen black? Why is my iPad not working? Why is everything falling apart? There we go. Everything is fine. All right, so same idea for this next one. All right, so we're looking at the change from 70 to 34. So 70 to 34, that's change of 36, I believe. All right, so that's 36. 34 to 16, what is that, 18? sure because you never know. Yep. Minus 18. All right, then minus 6. And we have no change here, so that's plus 0. All right, so we don't have a clear consistent change, so I'm going to do another level of change. So I'm going to go from negative 36 to 18, so that's actually adding 18. And then negative 18 to negative 6, that's adding 12. And then negative 6 to 0, that's adding 6. So that was my second difference, and I still do not have the same change, which means I'm going to go to a third difference. So here I have 18 to 12, which is negative 6, and then 12 to 6, which is negative 6. So here, now we have a clear, consistent change, but this didn't happen until the third difference. All right, so because it's now a third difference, that's what makes this cubic. So this is going to be add and third difference, which is your type. No, this is the function pattern. The type is cubic. All right, so now we need to do a regression model for a cubic function. So I'm gonna go back over to my calculator. All right, so now I want to copy and paste all the table information into calculator. So I need -4, and -3, -2, -1, and 0. All right, and then 70, 34, 16, 10, and 10. I'm doing a cubic regression, so this is going to be F4. And this is going to give you a very weird screen. All right, so here's the thing. I did this problem on purpose because of this screen. So we have negative 0.9999999. So that is a non-repeating or a non-terminating decimal, which is the same as -1. So we're going to have, I'm actually going to make note of this on the side. So we're going to have an A value of -0.9 that's not repeating. Then we have a B value of 2.73 times 10 to the -12. And we have a C value that is 1 and a D value that is 10. All right, so I'm going to come back over here to the iPad and kind of go back and analyze what all this means. Listen, hello. Okay. So this is what the calculator screen kind of spit out at us. So -0.9 repeating is the same as just -1. Now this 2.73 times 10 to the -12, that's the same as 0. The number is so small, it's not significant. And then we have a C value of 1 and a D value of 10. So when you're writing your equation, I'm going to kind of fill in the gaps. So -1 x cubed plus 0x squared plus x plus 10. So really what this equation is y equals -x cubed plus x plus 10. So we don't even have to write the squared term just because the coefficient is 0. And then we don't have to write the 1 at the very beginning. We don't have to write it at all. So this is your equation. So -x cubed plus x plus 10. All right, so that's kind of the gist of the different regression models that you're going to see. Now, the questions can be asked in a different way, though. So for example, I could actually give you a set of coordinates. So the only difference here is then you have to set up the table yourself. So it just really just adds one organizational step. It's not even really mathematical. All right, well, I can't draw a line. It's fine. Okay, so I'm going to draw it to give yourself plenty of room. So 0 all the way to 5. All right, and then we're going to have 8, 3, -4. Then -13, -24. Is it -37? Yeah. All right, so this is what we're looking at. So it's still a table. It's the same idea. It's just going to be set up a little bit differently. All right, so from the table, from 8 to 3, it's going to be -5. And then 3 to -4, that's -7. Then it's -9, -11, and -13. So whenever you see like every other consecutive integer, that's usually a good indicator it's going to be a second difference. So if I do another difference, -5 to -7 is -2, -2, -2, -2. So we have a clear change when we do a second difference. So because that's a second difference, so add and second difference. All right, so that means this is going to be quadratic. All right, and I'm just going to do the regression over here on the side. All right, so 0, 1, 2, 3, 4, 5. So 8, 3, -4, -13, -24, -37. This is quadratic. So your equation that you're going to get out is going to be y equals -x squared minus 4x plus 8. All right, so just to save time on the video, I'm just going to go ahead and do the regressions on the side. If you need the steps, feel free to rewind, go back to the first 4 problems I did, or you could even look here at the steps so you can kind of see what I did. Remember, I have both the Casio and the TI steps. All right, so now we're here for number 6. I want to find what's the rule for the function represented by the ordered pairs. Okay, so same idea. I'm actually going to see if I can just copy and paste this table so I don't have to redo it. There we go. Just on the off chance I have to do a bunch of differences, I'm going to move it over to the left. All right, so the x values go from 0 to 5. So 1, 2, 4, and 5. All right, and then I need the y values. So 4 to 10. And 34, 80. I believe it was 154. Yes, okay. So once again, I'm just gonna do all the differences here on the table, and then I'll do the regression on the side. All right, so to go from 4 to 2, that is -2. To go from 2 to 10, it's +8, then +24. Let's say that was 46. Math is hard. It's been a long day. Yep, 46. I'm always second guessing myself. Okie dokie. And then 154 to 80, was that 74? Yeah. Okay, so first difference didn't work out. So it's not add, it's not add multiply. So it has to either be quadratic or cubic. So now I'm going to do another difference. So to go from -2 to 8, that's +10. So then from 8 to 24, it's +16. So 22. Yep. And then that is 28. I believe so. Let me double check because math is hard. Yep. All right. And that's the second difference. Still no go. We need a clear, consistent change in that last column. So I'm going to go again. So 10 to 16 is +6. 16 plus 6 gives you 22. 22 plus 6 gives you 28. Now that we have a clear, consistent change, that is a third difference. So over here, your function type is going to be add. And third difference all right, which means it's going to be cubic. And then the regression, I'm going to do over here on the side. All right, so 4, 2, 10, 34, 80, and 154. All right, so our regression here is going to be y equals x cubed plus 2x squared minus 5x plus 4. So the table is really where everything's going to come into play. You have to look at the table. All right, so now we have a few applications, or just two. So this first one here is dealing with what we call fractals. So if you ever deal with like kaleidoscopes, that's what fractals are, which is math. So it also kind of goes into something similar called tessellations. But anyways, so with fractals, table shows the number of new branches in each figure of the pattern. They want to know what is a pattern you can use to complete the table and represent the relationship using words and an equation. Well, we don't need the words part. We're going to pretend that's not there. All right, so looking at the table here, one branch is going to transition into 3 branches. So if there's another change, each branch is going to transition into 3 more branches. So this is kind of like what kaleidoscopes do. All right, so they have the first 3 terms already laid out for you. So emphasis on the fact that it splits 3 times, which means that's what your multiplier is. So times 3 times 3. So 27, if 27 branches branch 3 times, or branch into 3 objects or 3 other branches, we're going to have 81 total branches. And if those 81 branches branch into 3 more, we're going to have 243 branches. So this is an add multiply pattern. So an add multiply pattern is going to follow an exponential pattern. And then your rule here is going to be y equals 3 to the x. All right. And over here for number 8, so the table below shows the fractions A of the original area of a piece of paper that remains after being cut in half n times. Find the function pattern, function type and regression equation that represents this data. All right, so we're looking at the change here. So between 1, 2, 3, and 4, well, that's plus 1. However, to go from 1/2 to 1/4 to 1/8 to 1/16, that is actually being multiplied by 1/2. So I'm constantly cutting that piece of paper in half. All right, so because we have an add multiply, that's going to follow an exponential function. And our function here is going to be y equals, oh my gosh, 1/2 raised to the x. All right, so here's kind of a really good part right here. So will the area ever equal 0? So you also have to justify it. So I'm actually going to show this part in the Casio, or in the calculator. So exit, menu, I'm going to go to table, and I'm going to plug in the function. So parentheses, 1/2, parentheses, raised to the x. So we want to see if the area is ever going to equal 0. So if I haven't cut the paper at all, it's just equal to 1. then it's just going to keep getting cut in half. However, as I keep cutting this piece of paper, you want to ask yourself, do any of the y value entries say 0 exactly? Because here's the thing. The size of the piece of paper can eventually even reach the size of like a fingernail, or even like a single cell of bacteria, or even the size of an atom. But there's still a piece of that paper there. So this kind of goes into the idea of an asymptote. So it gets closer and closer and closer and closer and closer to 0, but it never actually equals 0. So in this case, it does not ever equal 0. It's only going to get closer and closer to 0. All right. So my iPad will get its life together and I can finish this one. All right, so will the area ever equal 0? No. So it will get closer and closer, but will never actually equal 0. All right, so kind of a bonus here is it's the idea of an asymptote. And the actual asymptote here is y equals 0. It's getting closer and closer to 0, but it never actually equals 0.